like to welcome to Dr. Thayane Nepel, also from the Advanced Energy Storage Division here at UNICAMP. So Thayane is going to talk about overcoming challenges in lithium-ion batteries operation. Thank you, Thayane.
Thank you. Good afternoon, good night, and for everyone. My name is Thayane, like Ana Flavia presented. I am a postdoc at the Advanced Energy Storage Division at CINE, working with Professor Rubens and Gustavo. And I'm going to thank you for the opportunity to present in the conference. And I'm going to present some of the results of our research group in the way to overcome field challenges of lithium-ion batteries operation. And starting with a brief contextualization about the energy storage devices. The increasing energy demand, the global warming, and the finite oil reserves leads to a continuous development of the energy storage device. And in this scenario, lithium-ion batteries are a promising technology with a theoretical capacity several times higher than the established lithium-ion battery. However, the practical performance are really far from, including the capacity and the cycle life that are really big challenges. And to overcome all these challenges, we usually study the cathode is one of the most studied in the literature battery components, focusing on the improvement of oxygen diffusion and the catalytic performance, mainly for the charge reaction. For example, using the metallic catalyst to decrease the overpotential. The anode usually is metallic lithium, although its compatibility with the electrolyte is other issue. And about the electrolyte is one of our line. We study the stability and also the addition of ionic liquid, as Cheyenne explained before, and also water to improve the battery's performance. And besides, we studied the operation condition related with the oxygen supply, because it's a really important parameter to be understood and optimized, focusing mainly for practical application. And it's reported in the literature regarding the operation condition that the oxygen pressure increased the battery performance due to the enhancement of the diffusivity and oxygen concentration in the electrolyte and air electrode. Other approach is to study and evaluate the possibility to make holes over the cathode and analyze the open ratio. And the flow over the cathode is another object of study, and it's reported in the literature an option of electrolyte loss due to this flow fast enough to avoid complete cathode porous blocking due to the peroxide deposition, and appropriately slow to promote the oxygen reduction reaction. And for practical application, the humidity in the air and the water in the electrolyte is an important point to be understood and solved. The literature presents some controversial results depending on the air electrode and the electrolyte, but the best results indicate that water could really improve, could be promising for the battery's performance, especially when combined with catalysts, for example, ruthenium. But what's the operation condition to enhance the performance of the batteries, and how the pressure combined with the flow influence the capacity and cycle life? Could the operation condition affect the discharge products? And could the water even improve the performance? These are some questions that I'm going to present our results for them. Here, it's the first results that I'm going to present using a radially orientated multi-walled carbon nanotubes produced by chemical vapor deposition method and functionalized with oxygen plasma. And we evaluate the influence of oxygen continuous feed during the battery operation. Here we have the two possibilities of operation that we studied, the open one, where we have the flow during all the performance tests, and the closed when we have the feed in the beginning, and then during the performance test, we have a completely closed system. And comparing the two setups, the operation condition called as closed showed the best discharge capacity. It was possible to achieve near the double of discharge capacity. And we also verified the formation of different discharge products, chemical discharge products, based on the operation condition. Besides, the chemical composition of discharge products, including the lithium hydroperoxide formation in the closed system, decrease the charge of potential, favoring the charge process. And in this slide, we also studied the influence of the operation condition using CINE painted on carbon paper substrate, and applying a design of experiment. We also statistically analyze the influence of pressure in the closed condition and the combination of flow and the pressure when working in the open condition. In addition, we evaluate how the solvent could influence the capacity and the cyclability, considering the operation condition. Our results point out the same tendency that I showed before. Using the MSO, the closed condition gives the better results. And here we achieve even better capacity values, up to 22,000 million per hour per gram, and up to 26 cycles of 1,000 million per hour per gram. And in addition, the pressure combined with flow started by Doe, showed that the flow in the open system combined with the pressure decreased the performance due to electrolyte loss, and it was verified mainly for the DMSO solvent due to its higher volatility. So this analysis also points out the higher performance when using the DMSO as solvent with a lower over potential and also a higher discharge capacity and cyclability. And the DMSO leads to the best results due to the higher ionic conductivity, oxygen solubility, in addition with the absence of the reaction with lithium anode compared with tagged mist solvent. And using all these optimization of operation condition, we verified in a study adding water as additive, how we could get near the practical applications, more near than to practical applications. And using the optimal conditions, so closed operation, using 3 bar of pressure, and the MSO as solvent with lithium perchloride, and only the substrate carbon paper as air electrode, we verified that the addition of water, especially 550 ppm of water, allows 30 hours more of the discharge. So we verified an optimization adding this amount of water in a systematic study that we are concluding, and it is indicating that this is really correlated with the morphology of the product. So the characterization indicates the formation of mainly lithium peroxide and lithium hydroxide with deep changes in the morphology by water addition. We got deep discharge improvement and also cycle life. And with 550 ppm of water, we have up to 32 cycles of 2,000 million per hours per square meter. It's about 16 hours one cycle. And in this optimum point, adding 550 ppm of water, we verified the formation of toroids. And in the other concentrations, we have other morphologies, and after and before, with lower addition of water, we have especially films over the surface. So as conclusion of the results presented here, we bring that closed system provides an appropriate oxygen supply, conducting to an optimum of capacity and cyclability, especially when using the Nepel and lithium perchloride as electrolyte. And we can go even better with water addition, and so we can promote better discharge capacity and cyclability. We even using only carbon paper without any electrocatalysts. I think all our research group, a really partner team, especially the research that developed this work with us, Julia, Bruno, Martin, and Thayane. And our group thanks for the fellowship of FAPESP, Shell, support of the division CINE Center, and also CAPS and FEQ, CINE panel and LS for the characterization, and UNICAMP and FEQ. Thank you.
Thank you, Thayane. If you have questions here. So let me ask you about this, the effect of water in your electrode. So do you think that at the end, the water is actually affecting the morphology?
Yes, it's reported in the literature for other kinds of electrodes and also electrolytes. And we are trying to understand what is the optimum and what is the morphology changing with this water addition, but it's really affect the morphology. We have in the beginning, when we have 25 ppm of water, a film, and as we increase the amount of water, we nucleate, giving the toroids as mainly morphology. And when we go more than 550 ppm, as we verified up to now, we don't have more only toroids. We beginning to have more films together with the toroids.
Interesting. And just a curiosity, because it's not my area. But when we mean closed system or in an open, when we like close it, it's like you inject some oxygen and you close the system. That's
yes,
right?
Exactly.
And you open when you let the air like flowing through the battery.
Not
that's it.
Yes, not the air. Here we have just oxygen, so we have oxygen. A line. Yes, here we have just oxygen, but the open operation is like when we have a flow continuous going inside over the cathode. So here we have a continuous flow of oxygen over the cathode.
Okay. Okay, thank you, Thayane.